The potential energy of a particle moving along x-axis is given by U is equal to 5x square minus 20x plus 2 joule, where x is the coordinate of the particle in meter. If particle is released at x is equal to minus 3 meter, then we need to find that which one of the following options are actually correct. Okay, it is very much clear that the potential shall have the minimum value at the point where this differential will come out to be 0. So let's have it. Du dx, it is 10x minus 20. If we equate this part to be 0, we are getting this value x to be equal to how much? 2. That means at point x is equal to 2, the potential shall have the minimum value. And how much is this minimum value is? Put the value here, x is equal to 2, will be getting 20 minus 40 plus 2, or effectively minus of 18 joule here, potential energy at x is equal to 2. So now it's been said that the particle is released at x is equal to minus 3. That means 5 point along this side. This is the x is equal to minus 3. So how much is the potential energy at this particular point? X is equal to minus 3. It will come out to be 5 into 9 minus 20 into minus 3. That means it will be plus 60 altogether and plus 2. It is 107 joule. Okay. Now at this point the potential energy 107 joule. So now let's see what is the question here. Maximum x coordinate of the particle is, that means it will now shift 5 unit from here. So this was already how much? 2. So 5 unit from here, that means it will come out to be 7. So our option B is the correct answer. Maximum kinetic energy of the particle is, at this point the potential energy was 107 joule and here it was how much? Minus 18. So total change in the potential energy will be equal to gain in kinetic energy, and since it is starting with a 0 kinetic energy here, I would say the maximum kinetic energy will be equal to, add 18 here, it will come out to be 125 joule. So option D is also the correct answer for question number 6. So finally we got B and D as the correct answer. Now let's proceed to question number 7. In question number 7, a non-conducting cell of inner and outer radii R and 2R respectively has a charge Q uniformly distributed in its volume. Then what we know from a standard answer, that if there would be uniform volumetric charge distribution, then only the field here that comes out to be directly proportional to the function of R. But here we are having one cavity inside the region. So definitely at any particular point the effect of this much part has to be subtracted, and so we shall not be getting the field to be directly proportional to R. In fact, if you make a calculation, you shall have here E dot ds, that will be 4 pi r square must be equal to Q inside. Q inside will be from this much of the region, Q inside divided by epsilon naught. Since Q inside will not come out to be the direct function of RQ, so option B will not be the correct answer here. Similarly, electric potential in region R and 2R is directly proportional to R. Now it is very much sure that this particular function is not coming out to be the direct function of R or a constant term. So in that case, the integral of this particular value of E will certainly not come out to be directly proportional to R. So option C would also be the wrong answer. Now let's see the option A and option D. Electric field in region small r less than capital R is 0. Definitely it is not enclosing any charge here, and it is symmetrically distributed about this point. So electric field inside the region will definitely be 0. And electric potential is constant. Since electric field here at every different point is 0, so electric potential will come out to be a constant function. So for question number 7, we are getting option A and D as the correct answer. Now let's proceed to question number 8. Here in question number 8, in a cylindrical region, a uniform magnetic field is increasing at constant rate alpha Tesla per second. A particle of charge minus q is moved slowly to infinity from point O. Then work done by external agent is. The field at this particular region or anywhere at this region, the field would be in a circular way. That means, let's say I'm calculating the field here at distance r0. I would say E into 2 pi r0 must be equal to pi a square into dv dt, that's been given to be alpha here. So I'm getting this value of electric field is a square alpha divided by 2 r0, and it will be along this direction actually. So if the particle has been taken from this point along this direction, let this angle is theta. So charge particle being negative, that means internal force will try to act along this direction, and so external agent has to exert the force in this direction, and the work done is positive by the external agent. Now at this point the electric field will be along this direction. So this angle theta, so definitely this will be how much? Theta itself. So the work done here, I would say q, that is magnitude of charge here, value of E at this distance r, it will be a square alpha divided by 2r here, and this angle is theta, so I shall say it is cos theta. That means it will be r0 divided by r, and let this change at this point is dy, so it will be dy. Integrate this function, that will give you the value of the work done here. So I would say q a square alpha r0 divided by 2 integral of dy divided by r square. R square itself is r0 square plus y square. This distance is y actually. Integration of this function is how much? It will be 1 by r0 tan inverse y by r0. So the total work done, it will be q a square alpha r0 divided by 2, it is 1 by r0 tan inverse y by r0. Limit has to be taken from y is equal to 0 to infinity. So we'll be getting this work done as q a square alpha by 2. This r0 will cancel out, and here putting the value of y to be infinity, we shall be getting here the value to be how much? Pi by 2. So simply it is pi and 4 here. So we are getting the answer as pi q a square alpha divided by 4. So for question number 8, option C is the correct answer. Now other one being, if the particle would be moved along this direction, then at every time the electric field is perpendicular to the direction of the motion of particles. So essentially the work done will be 0. So option A is also the correct answer. So finally A and C are the correct answer for question number 8. Now let's proceed to question number 9. In question number 9, a metal A is exposed to photon of wavelength 292 nanometer. The ejected electrons have maximum kinetic energy as k1 electron volt and smallest de Broglie wavelength of lambda. When photon of wavelength lambda 2 is equal to 264 nanometer strike the surface of metal B, the ejected photoelectrons have maximum kinetic energy k2 as k1 minus 1.5 electron volt and smallest de Broglie wavelength is 2 lambda. Then we need to evaluate which one of these given options are correct. Okay, let's start with the situation given for metal A. The wavelength incident is how much? 292 nanometers. So I would say HC divided by 292 nanometer minus 5.1 would be equal to the maximum kinetic energy K1, and similarly for B it would be HC divided by 264 nanometer minus phi 2 would be equal to how much? It will be K2. Other part that actually being given here, it is the smallest de Broglie wavelength. That means lambda is equal to h divided by root under 2 mk for metal A, and it will be 2 lambda is equal to h divided by root under 2 mk2 for metal B. So just have this calculation here. We'll be getting 2 would be equal to square root of k1 divided by k2, or k1 is equal to 4k2. But one more function that actually was given here, that was k2 is equal to k1 minus 1.5 electron volt. That means I would be saying k2 must be equal to 4k2 minus 1.5 in electron volt, or simply 3k2 is equal to 1.5 electron volt. That means k2 is equal to 0.5 electron volt, k1 is equal to, it is 4k2, 2 electron volt. Now on this particular calculation here, HC divided by 264 nanometer, that means 1242 divided by 264 minus k2. K2 was how much? It was 0.5 electron volt. This will come out to be the value of phi 2 here, and this value is 4.2 electron volt. That is the work function of metal B. Similarly, for metal A, it is 1242 divided by 292 minus k1. It was 2 electron volt. This time we'll be getting this value of phi 1 to be equal to 2.25 electron volt. So looking onto the options, option A, option B and option C are the correct answer for question number 9. Now we shall proceed to question number 10. In question number 10, a resistance R and a capacitor of capacitance C are connected in series to an alternating source having EMF V is equal to V0 sine omega t. It is given that omega is equal to 1 by square root of 3 RC. Then let's first try to calculate the impedance of the circuit. For that, we will start with the value of calculation of capacitive reactance. It will be 1 by omega C. That means 1 by C here, and the value of omega was how much? It is 1 by root 3 RC. So we are getting this value to be root 3 R. So Z will be how much? It will be 2R. And the phase angle, definitely it would be root 3 R divided by R, that is coming out to be root 3. So tan inverse root 3 is how much? Pi by 3. Pi by 3. So current I would be V divided by Z, or V0. Z was 2R sine omega t. This is capacitive circuit, so the phase will be pi by 3 here. Clearly option A is the correct answer here. Current through this one will be the wrong statement. Now the average power, it will be IRMS, that is V0 divided by 2R, VRMS, V0 itself divided by 1 by 2 into power factor, that is cos of pi by 3, it is 1 by 2. So altogether we are getting this answer as V0 square divided by 8R. So clearly option C is the correct answer. So finally for question number 10, option A and C are the matching answer. Now let's proceed to question number 11.